Okay, so we are going to try and use our second derivatives test to find the local minimum, local maximum, and saddle points of a particular function. And you can have more than one local maximum or local minimum. It just depends on how many critical points that you have and how many of them satisfy which condition of the second derivatives test. So let's start by finding critical points, because that's always your first step. Here's my function, f of xy equals 2 minus x to the fourth plus 2x squared minus y squared. So what is fx? Fx is going to equal negative 4x cubed plus 4x, and that's it. I can see that I would probably want to factor this. Let's factor a negative 4x out, which would give me x squared minus 1, or negative 4x, x plus 1, x minus 1. Okay? If we set that equal to 0, because remember, that's how we find critical points. We set our partials equal to 0. Then this will have three solutions, x equals 0 or plus or minus 1. Okay? Now let's go to our fy. What is fy? Y only shows up in one term here, so the partial would be negative 2y. If we set that equal to 0, that implies that y is equal to 0. And now we have three critical points. So critical points are 0, 0. So basically I'm taking all combinations of x's with y's. 0, 0 would be one of them. 1, 0 would be one of them. And negative 1, 0 would be one of them. Okay? Next thing I need to do is compute all of my second partials. So fxx, what is that? Well, here's fx. Let's take the derivative of this with respect to x. That's going to be negative 12 x squared plus 4. What is fyy? Fyy is equal to the derivative of this with respect to y. That's just negative 2. And then what is fxy? Well, remember, fxy, you can either differentiate this one with respect to y or this one with respect to x. But in either case, you should be able to see that that mixed partial gives me a 0. All right? So now how do we compute d? Well, let's do this in three different cases, because I need to test each one of these critical points by plugging them into that d. So let's start by looking at d of 0, 0. Okay? Remember, d of 0, 0 is fxx times fyy minus the mixed partial fxy squared. So that's going to be negative 12 times 0 squared plus 4 times negative 2 minus 0 squared. That's what that would look like. Now, this is equal to 4 times negative 2, which is negative 8, minus 0. That's equal to negative 8, which is a negative number, less than 0. Okay? What does that mean for us? Well, one thing I need to do is also check fxx at 0, 0. Because remember, the second derivatives test has us checking both the discriminant and the sign of fxx. Although, we just found that d is a negative number. So in our second derivatives test, if d is negative, that's the one case where we don't care what's happening with fxx. We can actually skip that, and immediately we know that 0, 0 is a saddle point, according to our second derivatives test. Okay? Now I need to compute the other two values. So d of 1, 0, what would that be? Okay? In this case, I'm looking at negative 12 times 1 squared plus 4 times negative 2, and I'm just going to skip writing the minus 0 squared. I know that that's not going to matter. So what is this equal to? This is equal to negative 12 plus 4, which is negative 8 times negative 2, which would be positive 16. That's greater than 0. So because d is greater than 0, now I have to check fxx of 1, 0 and see what's happening there. Well, fxx is this guy. And we've already plugged negative 12, we've already plugged 1, 0, 0 into negative 12x squared plus 4. That's this step right here. This gave us negative 8 when we did that. Negative 8, a negative number. So if d is positive and fxx is negative, what do we get from that? Positive d, negative fxx is a local maximum. Okay? So that tells me that 1, 0 is a local max. I'm kind of squeezing this in. I didn't leave myself a ton of space in this problem. Let's do the same thing with the other point, d, negative 1, 0. Now notice something. The only place I actually plug an x in to any of this is right here, and I'm squaring it. So negative 1 squared is going to give me the same thing that 1 squared is going to give me. That means if I plug negative 1, 0 into my discriminant d, I should end up with the exact same thing that I got here, 16, which is greater than 0. And we're still going to have fxx of 1, 0 equal to negative 8, which is a negative number. So that means negative 1, 0 is also a local max. Okay? That's how we use that second derivative test. All right. Let's take a look at another couple of problems where the optimization that we're doing is not just for some arbitrary function, but there's some physical or interpretive context that we could come up with. So what I want to do in this problem is find a point on this plane, x minus 2y plus 3z equals 6, that is closest to the point 0, 1, 1. Now you actually have a technique for doing this. In chapter 12, we came up with a technique for this using projections. And you could technically use that approach here. In fact, it's a good exercise to do that and compare your result to what we're going to get by using this optimization technique. You should get the same thing. But for us, what I want to do is think of this in terms of distance formula. So first of all, notice that I could isolate the x in this plane and write it as x equals 2y minus 3z plus 6. And the idea there is that a point on the plane has the form 2y minus 3z plus 6y z. Does it make sense why I did that? Because any point on this plane has to satisfy this equation. But if I've isolated the x, it gives me an expression in terms of y and z that I can substitute for where x would normally appear. So all the points on my plane are going to have this form. And the reason that I did this is I'm now only concerned with 2 variables instead of 3, y and z, instead of x, y, and z. So if this is a point on my plane, how do I compute the distance between this point and the point 0, 1, 1? Well, that's what distance formula is for. And notice, distance is now only going to be a function of y and z. Y, z. Okay? Distance formula is going to give me the square root of this minus 0 squared. So that's 2y minus 3z plus 6 squared, y minus 1 squared, and z minus 1 squared as well. So I have plus y minus 1 squared plus z minus 1 squared. Okay? Now I can, this is the function that I want to optimize, and in particular, I want a minimum value for this function. However, This function is cumbersome to work with because of that square root. And we're going to use something, a couple of things in this problem where we can bypass difficult work by thinking logically about the problem. If I'm looking for a minimum distance, then the minimum distance that I would get from this distance formula is going to be the same as the minimum squared distance. So what that means is I'm going to be looking at the square of this function instead. Okay? Which gets rid of that radical for me. And think about that logically for a second. We actually use this idea in Calculus 1 sometimes for similar optimization problems. Whatever minimizes this function will also minimize this one. Okay? Because if I find the smallest squared distance between a point and a plane, the same point would give me the minimum distance. So I don't know, I feel like I'm talking in circles, but hopefully intuitively that makes sense. Let's minimize this function now. Okay, so to do that, I need to find critical points. Dx, d squared of x, is equal to what? Well, I'm differentiating this with respect to x, so I'll get a 2 that comes out and a negative 3 that comes out as well. So for that, oh, I'm sorry, it's not x. I'm forgetting what my variables are. dy and dz are what I'm looking for. We don't have an x anymore. I need that to be a y. So differentiate with respect to y first. That's going to look like 4 times 2y minus 3z plus 6, and then plus 2 times y minus 1, and then that term's going to go away. This is equal to, when we simplify things down, after doing some distributive and combining like terms, 10y minus 12z plus 22. Okay? And then if I look at dz squared, what is that going to look like? Well, that would be, differentiating with respect to z now, this guy, negative 6, 2y minus 3z plus 6. This term is going to go away, and then this guy is going to become plus 2z minus 1. Distribute so that we can combine like terms, and I get negative 12y plus 20z minus 38. Now, what's the point of finding these partial derivatives? Well, the goal is to find critical numbers, so we set each of those equal to 0. Now, if you notice, together these two things create a system of equations. So I could write this as 10y minus 12z, let's subtract the 22 over, so negative 22, and then negative 12y plus 20z equals 38. This is a system of two equations in two variables, and you can use techniques from Algebra 1 to solve this. Okay? I am not going to go through the steps of solving this system because that's something that you should be able to do. For the sake of time, I want to just give the solution. If you solve this system of equations, what you should get is y equals 2/7 and z equals 29/14. Okay? All that remains is to find the value of x that would give us the point that we're looking for. Okay? But we have an equation that relates x to y and z. So I'm going to plug these y and z values into that. So x is equal to 2 times y, which is 2/7, minus 3 times 29/14, that's our z, plus 6. Skipping the lengthy arithmetic there, we should end up with a value of 5/14 as our answer. And so that means the point that we just got out of this work, so 14, is 5/14, 2/7, 29/14. Okay? Now I'm going to say done. And you might look at that and think, well, how do I know that that's the correct point? Because we are told that we want the point on that plane that is closest to 0, 1, 1. And what I found was a function that gives me the square of the distance between any point on the plane and the point 0, 1, 1, which like we kind of argued, would if we minimize that function, we would get the same point as if we minimized this one. And all I did was get a critical point. I didn't find any way of determining whether this point was a local minimum, local maximum, or saddle point. I would need the second derivative test for that normally. But if we think about this in a logical way, if you consider a plane and some point that's not on the plane, we know that there is a shortest distance to that plane, but there is no longest distance, because I can continue picking points further and further and further and further and further away from this point, and that would imply that there is no maximum distance, because that plane goes on forever. So there's no possible way for this thing to represent a local maximum. It also can't represent a saddle point, because kind of by the same logic, any critical point that we get based on what we know about points off of planes should represent a minimum. So we get to bypass a lot of that more lengthy work by using a little bit of logic to connect the dots here. Okay? All right, let me see. Okay. So that is a couple of examples. I'm going to do another one where we're looking at a rectangular box. You do problems like this in Calculus 1. And in this case, we're trying to minimize the surface area of a box, a rectangular box that has fixed volume. So for this, I'm going to assume that my rectangular box has dimensions x, y, and z. Okay? Now, we're told that the volume of this box is equal to 1,000 cubic centimeters. And the volume of a rectangular box can be found by multiplying all three dimensions. X, Y, Z is equal to 1,000. Okay? That's what we know just from our given information. The function that we want to minimize is surface area, which I'm going to call S. Surface area would be the sum of the areas of all six faces, which would be 2xy plus 2xz plus 2yz. Now the issue, this being the function that I want to minimize, this function has three variables, x, y, and z. And so far we only know how to minimize functions of two variables. So we're going to do something that you do a lot of in optimization problems in Calculus 1, which is make a substitution to reduce this thing down to a function of only two variables. And this constraint up here is where that substitution is going to come from. Let's solve this thing for one of these three variables. Let's just say z. It doesn't matter which one you do, but I'm going to do z. Z is equal to 1,000 over xy. Okay? That gives me a substitution that I could use for the z's in this function. S is equal to 2xy. Plugging 1,000 over xy in for the z here, you'll see the x's cancel out. 2 times 1,000 is 2,000, so I'm going to get plus 2,000 over y. And then similarly over here, I'll end up with 2,000 over x. So this is my surface area function as a function of only two variables, x and y now. And this is the guy that I want to try and minimize. I'm looking for minimal surface area. So just like before, we want to find critical points that we can use. So I'm going to find Sx first.